Yeah, welcome back to our last topic in this unit, that is dealing with the PID controllers. So, interfacing sensors with control system PID controllers. A proportional integral derivative controller, PID controller or three-term controller, it is also known as three-term controller, is a control loop feedback mechanism widely used in industrial control systems and a variety of other applications requiring continuously modulated control. A PID controller continuously calculates an error value as the difference between a desired set point and a measured process variable, and applies a correction based on proportional integral and derivative terms denoted Pi and D uh, respectively, which give the controller its name. The first theoretical analysis and practical applications was in the field of automatic steering systems for ships, developed from the early 1920s onwards. It was then used for automatic process control in manufacturing industry, where it was widely implemented in pneumatic and then electronic controllers. Today, there is a universal use of PID concept in applications requiring accurate and desired automatic control. Control is widely used in all areas where control is applied. So it solves 90% of all the existing problems. So that is the beauty, or that is the advantage of PID controller. P depends on present error, I on the accumulation of past errors, D is the prediction of future errors. So, based on current rate of change. So, the importance of PID comes from these three factors. The characteristics PID controllers, the proportional controller is having KP, will have the effect of reducing the rise time and will reduce but never eliminates the steady state error. So steady state error is part of it. The integral control Ki will have the effect of eliminating steady state error for a constant or step input, but it may make a transient response slower. A derivative controller Kd will have the effect of increasing the stability of the system, reducing the overshoot and improving the transient response. In fact, changing one of these variables can change the effect of other two. With the PID controller, call set the PID value so that we will not have any over or undershoot and reach a set point directly. PID controller has all the necessary dynamics, fast reaction on the change of the controller input D mode, increase in control signal to lead error towards zero, that is I mode, and suitable action inside controller error area to eliminate oscillations, that is P mode. This combination of present, past, future makes it possible to control the application very well. So although a PID controller has three control terms, sonic applications usually only one or two terms to provide the tile appropriate control. So here this is achieved by setting the unused parameters to zero and is called a PI, PD or PRI controller in the absence of other control actions. PI controllers are fairly common since derivative action is sensitive to measurement noise, whereas the absence of an integral term may prevent the system from reaching its target value. So here this is the simple PID controller. This is the summer, and this is the function of T signal, and you have the summing from plus and minus. This signal is sent to both P, I and D, and then again it is summing up, and it sends the signal to plant or process control. So this is the simple PID controller logic. Some limitations of PID controller. So here, while PID controllers are applicable to many control problems and often performs satisfactory without any improvements or only coarse tuning, they can perform poorly in some applications and do not in general provide optimal control. The fundamental difficulty with the PID controllers is that it is a feedback control system with constant parameters and no direct knowledge of the process, and thus overall performance is reactive and a compromise. While PID control is best controller in an observer without a model of the process, better performance can be obtained by overtly modeling the actor of the process without resorting to an observer. So PID controllers, when used alone, can give poor performance when the PID loop gains must be reduced so that the control system does not overshoot, oscillate, or hunt above the control set point. So they also have difficulties in the presence of non-linearities, may trade-off regulation versus response time, do not react to changing process behavior. Say, for example, the process changes after it has wound up and have a lag in responding to larger disturbances. The most significant improvement is to incorporate feed-forward control with knowledge about the system and using the PID only to control error. Alternatively, PIDs can be modified in more minor ways, such as by changing the parameters, either gain scheduling in different use cases, or adaptively modifying them based on the performance, improving measurement, a higher sampling rate, precision and accuracy, and low pass filtering if necessary, or cascading multiple PID controllers. So this is about PID controllers and how to interface this to real world problems. So this is the last topic in this unit. Now we are completing this unit, and we have one more unit left out that we will discuss in next session. Thank you, students. Thank you.